Alright, welcome back everybody. This is video 2 for section 9.8 of AP Calculus BC. We're talking about finding the area of a polar region or the area bounded by a single polar curve. And let's continue where we left off. We finished example 2 at the end of the last video, and we'll start up with example 3 here. Find the area inside one petal of the rose curve, r equals 2 sine of 3 theta. The fact that it's saying there are multiple petals that we're going to be looking at here means that we're going to have some options probably as far as how we're going to do the integration to determine this area. So let's go ahead and we'll take a look at the curve. 2 sine of 3 theta. And let's see, my window is from 0 to 2 pi. I'm going to make my x and y values a little smaller since I know that the maximum value I can get out of 2 sine of theta is 2. So, alright, here, let's go take a look at what this looks like from 0 to 2 pi. Oh, from 0 to 2 pi, it traces the petals a couple of times. So we need to find the area of one petal. And by the way, it might not look like these petals are the same area, but that's just because of the graphics distortion. If I zoom square this and make the units the same size, you should see that those petals are all the same size on our little rose curve here. So we can pick any of the petals and find the starting angle and the ending angle in order to set up our formula for the area inside of a petal. So we're going to have 1/2 times the integral of r squared. Oops. And I'm going to trace this to find my endpoint. We start at 0. Start at 0. And we stop at 1.047, and that's the first petal here. 1.047 is pi over 3. So I can integrate this from 0 to pi over 3, and that'll give me the area inside of one petal of the curve. And so I'll break out my calculator and go ahead and do that. I've got 1/2 times the integral of the quantity 2 sine of 3 theta, quantity squared, with respect to theta, from 0 to pi over 2. Punch it in, and we get 1.571. Wait a second. Did I just do pi over 2? That should have been pi over 3. Whoops. Let's try that again. Oh, how about that? I don't know if you noticed, but the integral from 0 to pi over 2 resulted in an area of pi over 2 inside that curve, and the integral from 0 to pi over 3 results in an area of pi over 3. How about that? Interesting. Didn't notice that before. Alright, example 4 comes from the 2019 AP Calculus BC exam free response question number 2. We're going to incorporate some area ideas from today, as well as some other things that we've touched on in previous parts of this course. So let's go ahead and we'll look at this. Let S be the region bounded by the graph of the polar curve. R of theta equals 3 square root of theta sine of theta squared for the interval from 0 to square root of pi, as shown in the figure to the right. And so this is, it starts here at 0, and when it comes back here, this is at square root of pi. So we've got our limits of integration to find the area of S. All we need to do to set this up is limits of integration are going to be 0 to square root of pi. 1/2 times r of theta, quantity squared. And since this is a calculator section, we're most definitely going to be finding this integral using our graphing calculator. It would be silly not to. And so we've got 1/2 times the integral of the quantity 3 square root of theta times sine of theta squared. That whole quantity squared with respect to theta from 0 to square root of pi. Let my calculator chew on this for a moment. That's one of the hardest things about doing these problems for me is the weighting for my calculator. So we end up with 3.534 as the area of the region S. Now part B has nothing to do with area. It says, what is the average distance from the origin to a point on the polar curve? Okay, for 0 to pi, or to the square root of pi. Now, this incorporates a couple of different ideas. First of all, realize the distance from the origin to a point on the curve in polar form is just whatever r is. That's the distance from the origin to here is the r value there given by the function. Distance from 0 to here is the r value. So what this is really asking us is, it's asking us to find the average value of r from the origin to a point on the polar curve. So we're going to use our average value formula, and we're going to use r as our integrand. So average value 1 over b minus a times the integral from a to b, and we're finding the average value of r. So that's going to be our integrand. And we'll go ahead and punch this up in our calculator. So we've got 1 over square root of pi times the integral of 3 square root of theta times sine of theta squared with respect to theta from 0 to square root of pi. And we punch that up. And now we wait for the calculator to give us that distance. All right, and we get 1.580. 1.579 is also an acceptable answer since that's the truncated answer. But I'm going to go ahead and write down the rounded answer, 1.580. So that takes care of part B, the average distance from the origin to a point on the curve. Which really required me to understand two things. One, that r represents the distance from the origin to a point on the curve, and then two, to recall how to use the average value formula. All right, I'm going to go ahead and erase this from my picture because I'm going to put another line in there to help me with part C. Part C. There's a line through the origin with positive slope m that divides the region S into two regions with equal areas. Write but do not solve an equation involving one or more integrals whose solution gives the value of m. Now there are a lot of options for me as far as what to do here, but think about it. We're talking about some angle, some line that goes through here with a positive slope of m. Okay, so if the slope of that line is m, that means the equation of that line is, y equals mx in Cartesian form. But that means that the slope is equal to y divided by x. And y divided by x represents the arctangent of this angle. And so the angle here that this line cuts through is the arctangent of the slope. All right, so that's the angle theta. Now, why is that important? Well, that's going to be the upper limit of integration of our integral for our first region. So we would want one of these equations, 1/2 times the integral from 0 to arctangent of m of the function is equal to, oh wait, it's got to be squared, is equal to 1/2 times the integral from arctangent of m to square root of pi of the function. We could also write this equation where we multiplied both sides by 2 and didn't have the 1/2. We could also, since we found the area of region S in part A, we could take either of these halves of the equation and set it equal to half of the value that we found in part A. I could just say, 1/2 integral from 0 to arctangent of m of 3 square root of theta sine of theta squared is equal to half of, that's 1.767. I could get away with writing that too. Lots of different things I could write. All right, that takes us to the end of this example and the end of this lesson, and we'll see you next time for section 9.9, the final section of Unit 9 of AP Calculus BC. Have a great rest of your day, everybody, and we'll see you next time. Bye-bye.